All right, we are going to do a relatively quick video today. I'm going to show you how to derive a few equations from the graphs that we've looked at, mostly from the velocity graph. And I just want you to try and follow along and understand where everything is coming from. These equations are given to you on your reference sheet. You don't need to be able to derive these. The reason for this video is that you are going to start to see how we derive equations. Again, just like, we don't just read a graph and say what happened in the graph. We don't just use equations. We have to be able to create some on our own. Okay, so we've got to be able to use all of the tools that are available to us. And one of those things is to use our graphs in order to actually, get something from it, get an equation. So here we have a velocity time graph. This is for constant acceleration, straight line on this graph. It is a constant acceleration. And what we have is we have a couple of things on the graph. We've got this point here. They have it labeled U. I'm going to label it V sub 0, okay, meaning initial velocity. Over here, we've got the final velocity, which using some kind of College Board conventions, we're going to label this Vx. Okay, so we've got an initial velocity and a final velocity. We've got a time, t. Okay, and so if we want to write an equation for this line, y velocity equals mx plus b, right? Well, the slope of a velocity time graph is acceleration. So if we do this in y equals m slope, we're going to put in acceleration. X is time plus b. We get v sub 0. Okay, I'm going to rearrange this a little bit, and I'm going to show you it the way that the College Board gives it to you on the back of your reference sheet. So the reference sheet tells you that any v that you're looking for, we're going to call it v sub x. Okay, and that's this v sub x here. Acceleration, for some reason, they also like to put an x on it. And then time, and then we have Vx sub 0. Okay, so those are the way that the College Board writes out the variables. For some unknown reason, they flip-flop these two pieces. And a little bit of that is just that in general, kinematics equations for, since time has existed, have been written as your final velocity is your initial velocity, which should make sense, plus the acceleration that you are undergoing over how long. And that should make sense. That whole idea that I want to know the final velocity, well, I can start with my initial velocity and then just add on to it the change that was created by acceleration. Okay, because acceleration is change in velocity over time, right? So if this is change in velocity over time, and I multiply it by time, what I'm getting here is that I'm adding to my initial velocity the change in velocity. So it could be a positive, it could be a negative. This could be sloping up, it could be sloping down. But what you'll end up with is, at the end of this, your final velocity. Okay? All right, so that's the idea for getting the first equation on our reference sheet. The next equation on the reference sheet is a little bit harder. I'm going to go through it. Again, you don't really need to be able to do this. I just want you to try to follow along. Okay, so I'm going to erase this. We have the same variables as before. So we have v, we're just going to call this v sub 0. We have v sub x. And over here, we've got time. Okay, if I want to figure out an equation for the change in position, so delta x, remember, the area under the curve gives me the change in position. The area under a velocity graph will give me change in position. This velocity graph is a weird shape. It's got a triangle, this part here, and It's got a rectangle, this part here. So we need to take the area of both of those. So let's do the first one, the easy one, this little rectangle. The rectangle is length times width, right? So it's v sub 0 times t. That's our first area. That gives us this part here. Now we need the next part. So we're going to do this triangle, which is 1/2 times the base. The base is time. Okay, 1/2 base times height. Height is going to be Vx minus V sub 0. Now, if you look at your reference sheet, this is not what the second equation looks like. The second equation doesn't have Vx and Vo in it. It has an A. So the College Board likes to give you questions that say, derive an equation for this, but only use these variables. So if the equation said, derive an equation for change in position, but you may not use the variable v sub x, then this equation isn't finished. We can't have this in there. Okay, so we need to figure out a way to get rid of that v sub f, or the v sub x, okay, the final velocity. And so what we're going to do is we're going to figure out some way of changing this here into acceleration. Okay, we know that final velocity, v sub x, equals initial velocity, v sub 0, plus a t, right? We just did that. Okay, this is y equals mx plus b. So if we can take this and rearrange it, we can get Vx minus V sub 0 equals A t. Well, look at that. I have something I can plug in here and get rid of the V sub x. So now I have delta x, I apologize for writing with a mouse, equals V sub 0 t plus 1/2 t times a t, which is at squared. So this is actually plus, whoops, I'm getting messy here, plus 1/2 a t squared. And if you look at your reference sheet, which we're going to do now, okay, these are the equations on your reference sheet. So here is that first one, which is just using y equals mx plus b to get the equation. Here is that second one. Okay, it's not written exactly the way I just came up with it, but it's basically the same. X is your final position, XO is your initial position. You can really move that over and just say change in position. Okay, here's that initial velocity times time plus 1/2 acceleration times time squared. I did not derive this one for you. I could have, it would take a long time and you don't want to watch me anymore, but you're getting the idea of how to derive equations. Okay, so this is another equation. We're going to go through how and when to use all these during class, but the basic concept that you want to be looking for is what variables do you know and what variables do you have in your equations? If you notice, both of these have time in them. Okay, the first and the second equation. So if your question has time in there somewhere, then you can use these two equations. If it doesn't have time, you're probably going to end up having to use this equation. Okay, if it has final velocity in it, okay, you can use this one, but you can't use this one. This has no final velocity. Okay, so you can notice that the reason that we have three different equations here with relatively the same variables is that they're not the same variables. Something's missing out of each one. This one has no position. Okay, so you're going to have to be able to pick and choose which equation do I use when. Over here, the equations you should know for uniform accelerated motion. These are just things that should be memorized by you. Definition of velocity. Velocity is the change in position over time. Definition of acceleration. Acceleration is the change in velocity over time. Average velocity. Because we are using uniform accelerated motion, meaning that it's straight line velocity graphs, you can just take the final plus the initial and divide it by 2. And that will give you your average velocity. Okay. All right. I just wanted you to see some deriving equations, and then next class we will use these equations. Okay. Thank you.